The length of a king's forearm once decided the fate of empires. This is the story of measurement, and it begins not with science, but with sacred ceremony. By the end of this journey, you will see every ruler, scale, and clock as a chapter in humanity's boldest quest for truth. How did a fragile metal cylinder locked in a vault become the world's official kilogram, only to be dethroned by a constant from quantum physics? Why did ancient builders encode the solar year into the very stones of a pyramid? The answers reveal a hidden war between chaos and order, fought with numbers. What part of your daily life feels most defined by a simple measurement? The Nile's floodwaters were a force of both life and erasure. Each year, the river would swell, nourishing the soil but washing away every boundary marker, every line between one farmer's field and another's. From this annual chaos, a profound need was born. Re-establishing those lines was not merely administrative work. It was a sacred duty. In ancient Egypt, to measure the land was to participate in the cosmic principle of order, truth, and harmony. Measurement was the act of imposing divine balance onto a world prone to disorder. The tool for this holy task was the royal cubit, a length based on the forearm of the pharaoh, who was himself considered a living god. This standard was not kept in a workshop, but within temples, treated with ceremonial reverence. Historian of science noted that these measures were deeply intertwined with religious and astronomical beliefs. When an architect used the royal cubit to lay out a temple or a pyramid, he was not just building. He was aligning human creation with celestial patterns, weaving stone into the fabric of the cosmos itself. This perspective transforms our view of ancient monuments. They are not just tombs or places of worship. They are measured prayers, physical manifestations of a universe governed by sacred number and proportion. This idea echoes across other early civilizations. In ancient Vedic India, the concept was a similar cosmic order upheld through precise ritual and measurement. So, at its very origin, the act of measurement was a spiritual covenant. It was humanity's first attempt to read the blueprint of the gods and replicate it on Earth. But when a blueprint this powerful falls into the hands of kings and emperors, its purpose begins to shift from the sacred to the profoundly political. That black granite rod, the royal cubit, was far more than a tool. It was a physical law. Crafted to the exact length of the pharaoh's forearm from elbow to fingertip, it was subdivided with astonishing care into 7 palms, and each palm into 4 digits. This was the master key to the kingdom's geometry. Enforcing this single standard was a power held tightly by the priesthood and the pharaoh himself. To possess the official measure was to control commerce, to collect taxes, and to command the very shape of reality. This was measurement as an instrument of state, a means to translate divine authority into stone and order. Consider the sheer ambition of the Great Pyramid at Giza. Its base is a near-perfect square, each side originally measuring 440 royal cubits. The precision is staggering. Teams of workers, using nothing more than knotted surveying ropes, copper chisels, and sighting rods, achieved an error margin of less than 1/15 of 1%. But the intrigue deepens. Multiply the length of one base side by 4, and you get the pyramid's perimeter. Now, take that perimeter length and scale it up. If you imagine each cubit in the perimeter as representing one day, the total corresponds almost exactly to the number of days in a solar year. This is not likely a coincidence. It suggests the builders were encoding celestial time into terrestrial space, using their sacred unit to bind Earth to the heavens. This monumental project required an army of official measurers, specialists who translated the granite standard into the reality of the work site. Their role was societal glue. They ensured every block fit, every corridor aligned, and that the pharaoh's eternal statement in stone was flawless. The cubit built more than pyramids. It built the very idea of an empire defined by uniformity and control. Yet, for all its perfection within Egypt's borders, the royal cubit was a solitary island of order. Once traders sailed beyond the Nile, they entered a world of glorious, frustrating chaos. Every port, every kingdom had its own sacred forearm, its own divine foot. The dream of a single, universal language of measure was still away, waiting for a revolution not in stone, but in thought. While Egypt measured the earth, another civilization was mapping the sky. In the dust and heat of Mesopotamia, a Babylonian astronomer priest pressed a stylus into wet clay, recording the precise movement of Venus. His calculations did not rely on tens, but on a far more elegant foundation, the number 60. This was the birth of the Sexagesimal system, a mathematical gift that still quietly governs our modern world. Every time you check a clock or measure an angle, you are using a technology over 3,000 years old. Why 60? Its genius lies in divisibility. You can split 60 into halves, thirds, quarters, fifths, sixths, tenths, and more, a total of 12 different whole number divisions. For ancient astronomers dividing the circle of the heavens or merchants dividing sacks of grain, this was a practical miracle. It made complex fractions simple and trade more fluid. The unit of weight, the shekel, was itself defined by nature as a specific volume of barley grain, directly tethering their economy to the rhythms of agriculture. Scholar Otto work reveals how this system allowed Babylonian astronomers to create sophisticated mathematical models for predicting lunar phases and planetary motions. They sought a celestial order, and in doing so, they built a framework of numbers so resilient it outlasted their empire. Yet for all its elegance, this system could not impose unity. Each city-state, from Ur to Babylon, might use the same base 60 logic, but apply it to their own local standards for length or volume. Imagine a world where every town had its own minute, its own degree. This was the reality. The Babylonian legacy was a brilliant but fragmented language, a tower of numerical Babel where everyone counted the same way but measured nothing alike. This chaos of countless local standards would become the greatest obstacle to human cooperation, a puzzle that would demand a solution not from a king or a priest, but from an age of revolution. Step into a medieval marketplace, and you would be surrounded by a symphony of splendid confusion. A merchant from Flanders offers cloth measured in his local ell, the length from his elbow to his opposite wrist. A few stalls down, an English wool trader quotes a price per stone, but his stone weighs a different number of pounds than the stone used for weighing cheese just across the square. Land was not surveyed with a chain, but described by effort, an acre being whatever area a team of oxen could plow in a single day, a measure that changed with the slope of the field and the strength of the animals. This was a world where every measure was a living thing, tied to the human body, the local harvest, or the traditions of a guild. It was a system of profound local logic, but it created a wilderness of numbers where trust was the first casualty. A buyer from another town was at a perpetual disadvantage, ripe for deception simply because his foot was shorter than the seller's. In response to this rampant uncertainty, authorities made attempts to impose order. In England, the king's iron yardstick was established as the official standard for the yard, a physical bar kept in London. But its authority faded with every mile traveled from the capital. In distant villages, the local blacksmith's own iron rod, worn and stretched from years of use, remained the true law of the land. This was not mere stubbornness. In a world without rapid communication or easy travel, the local measure was the only tangible, trustworthy reality. The profound consequence of this chaos rippled far beyond the marketplace. It strangled science in its cradle. A brilliant experiment conducted in Padua could not be in Paris because the Florentine pound of mercury used in Italy bore no reliable relationship to the Parisian pound. Knowledge remained trapped in isolated pockets, unable to form a coherent, global picture of nature. The very language of quantity was a Tower of Babel, and it prevented humanity from having a shared conversation about the universe. This pervasive, frustrating disorder created a burning and universal desire. The old anchors, the king's arm or the farmer's daily labor, had proven too mutable, too human. The dream now was for a standard not drawn from authority, but borrowed from the cosmos itself, a measure so constant and impartial it could silence the cacophony forever. The cacophony of countless local measures finally met its match in the cold, clear logic of the 18th century. In the wake of the French Revolution, the newly formed Academy of Sciences was given a mission of breathtaking ambition. They were to erase the ancient, arbitrary standards of kings and replace them with a new unit born not from authority, but from nature itself. Their answer was the meter. Its proposed definition was a statement of pure, universalist idealism. 1 meter would be 1/10,000,000th of the distance from the North Pole to the equator, measured along a meridian line passing through Paris. For the first time in history, a unit of length would be a direct fraction of the Earth's own circumference, a standard literally drawn from the world for all the world's people. But to turn this beautiful idea into a physical reality required an epic feat of measurement. The task fell to two astronomers, Jean-Joseph and Pierre. Their mission was to triangulate the arc of the meridian between Dunkirk in the north and Barcelona in the south, a project that would consume 7 grueling years. This was not a quiet laboratory exercise. It was a grand, perilous expedition conducted against the backdrop of the Reign of Terror, and hauled delicate surveying instruments across the countryside, setting up observation towers on church steeples and hilltops. They faced suspicion from local villagers who saw them as royalist spies, bureaucratic delays, and the constant threat of political violence. In particular, endured immense personal hardship. An accidental error in his early calculations haunted him, leading to a period of deep despair and self-imposed exile in Spain, as he sought to verify and correct his work. Their story is one of obsessive dedication, a testament to the Enlightenment belief that through reason and meticulous observation, humanity could discover a fundamental truth about the natural world and build a better society upon it. When they finally completed their calculations, and the platinum meter bar was forged in 1799, it was more than a tool. It was a symbol. It declared that measurement belonged not to pharaohs or guilds, but to reason and to all humankind. This was the ultimate divorce of measurement from the sacred and the royal, anchoring it instead in the very geometry of our planet. Yet, for all its grandeur, this new anchor had a hidden weakness. The Earth, scientists would later discover, is not a perfect static sphere. It wobbles on its axis, its shape subtly deformed by gravitational forces. If the standard was a fraction of an imperfect and changing planet, could the standard itself be truly constant? The quest for perfection was not over. It had simply shifted its gaze from the soil beneath our feet to the immutable laws that govern the cosmos. The platinum meter bar was a line drawn from the Earth itself, a standard of pure geometry. But how do you capture a fundamental unit of mass, the very essence of matter, with the same cosmic elegance? The answer, for over a century, was surprisingly, profoundly human. In a high-security vault on the outskirts of Paris, resting under 3 nested bell jars, sat a small, shining cylinder. It was made from a special alloy of platinum and iridium, chosen for its hardness and resistance to corrosion. This object, known as the International Prototype Kilogram, was not just a reference. By international treaty, it was the definition. The mass of that little metal cylinder was, by decree, exactly 1 kilogram. Everything else in the world, from a bag of flour to the specifications for a spacecraft, was measured in relation to this one physical artifact. Think about the philosophical weight of that. A cornerstone of modern science, a unit used to calculate gravitational force, energy, and pressure, was ultimately defined by a thing you could hold in your hand. A thing that could, in theory, be dropped, scratched, or stolen. This created a vulnerability at the very heart of measurement. Scientists were acutely aware of the problem. They called the kilogram an artifact standard, and they knew artifacts could change. Even sealed in its vault, the prototype was not perfectly inert. Microscopic contaminants could settle on its surface. Cleaning procedures, however gentle, might remove minuscule amounts of metal. Over decades, these changes, though tiny, mattered immensely to the frontiers of precision science. To monitor this drift, a solemn ceremony was held every 40 years or so. Official copies of the kilogram, kept by nations around the world, were brought back to Paris for a grand comparison. The results were unsettling. When placed on ultrasensitive balances, the national kilograms did not all match the original or each other perfectly. And the differences were not static. They shifted over time. This presented a haunting scientific mystery. Was the original prototype in the vault slowly losing mass, or were the copies gradually gaining? There was no way to know for certain, because the object itself was the definition. You cannot measure the king against the king. This elegant cylinder, meant to be a permanent anchor, became instead a symbol of a beautiful, flawed ambition. It showed that the 19th century dream of perfect, immutable physical standards had reached its limit. The quest could not end with a human-made object in a glass case. To find true constancy, science would have to stop looking at things and start listening to the universe. It would need a standard written not in metal, but in the timeless language of physics itself. The little cylinder in its vault was a silent confession of human limitation. To build a system of measurement that could last for the ages, science needed to find something that never changed, something utterly indifferent to dust, time, or human error. This posed a profound question. What in the universe is truly, absolutely invariant? The answer was not an object but a behavior. It was written in the fundamental laws that govern existence itself. Scientists began to look to constants like the speed of light in a vacuum, the charge of a single electron, or the tiny number that governs quantum interactions, known as constant. These were not things you could put under a bell jar. They were properties of reality, as fixed and universal as the rules of mathematics. The pivotal moment in this intellectual shift came from Albert's theory of relativity. His work established that the speed of light is not just a fast number, it is a cosmic speed limit, a constant that remains the same for every observer regardless of how fast they are moving. This was a conceptual earthquake. It meant that a fundamental unit of length could be defined by how far light travels in a precise fraction of a second. The standard was no longer locked in Paris. It was beaming through the cosmos, accessible to anyone with the technology to measure it. This transition marks the final, complete secularization of measurement. It was the ultimate divorce from the sacred body of the king, from the soil of the earth, and even from the human-made artifact. The new anchors were the immutable laws of physics. This was also the ultimate democratization. A laboratory in Tokyo or heirs no longer needed a certified copy of a metal kilogram from France. They could, in principle, build their own apparatus and measure the constants directly, participating in a global conversation based on shared, verifiable truth. The stage was now set for a quiet revolution, one that would redefine the most basic units of our reality by tying them to the quantum heartbeat of the universe. On November 16, 2018, in a quiet conference room in Versailles, a vote was taken that changed the weight of the world. Delegates from 60 nations unanimously agreed to dethrone the little platinum cylinder forever. As of May 20, 2019, the kilogram would no longer be a thing you could touch. It would become a thought, a calculation, anchored to one of the smallest numbers in physics, constant. This was the final piece of a century-long puzzle to rebuild our entire system of measurement on the bedrock of quantum reality. But how do you trade a physical weight for a quantum idea? The answer is a device of breathtaking ingenuity called the Cubit balance. Imagine a classic balance scale, but with one side replaced by a coil of wire suspended in a magnetic field. Instead of adding weights to balance a 1 kilogram mass, scientists send a precise electrical current through the coil. This creates an electromagnetic force that lifts the mass, perfectly countering the pull of Earth's gravity. The magic happens in the measurement. By moving the coil at a constant, ultra-slow speed through that same magnetic field, they can measure the voltage generated with phenomenal accuracy. These two experiments, one with current and one with motion, allow scientists to calculate the exact relationship between the mechanical power needed to lift the mass and the electrical power used in the coil. That relationship is governed by constant. Think of it as establishing a cosmic exchange rate. We are trading the familiar concept of weight, the force of gravity on a mass, for a universal currency of action from the quantum world. Once that exchange rate is fixed by international agreement, the kilogram is defined. Any laboratory with a kibble balance can now realize the kilogram for themselves, without ever needing to compare it to a physical artifact in Paris. This is a liberation from the material world. It means the definition is now based on a constant of nature that is believed to be the same everywhere in the universe, and for all time. The meter had already a similar transformation back in 1983. It was redefined as the distance light travels in a vacuum in 1,299,792,458th of a second, fixing the speed of light as another eternal constant. Together, these redefinitions complete a philosophical revolution that began with the French Academy's dream of a natural standard. We have moved from measuring the macro world with macro tools, like carved rods and metal weights, to defining all our units through the invisible, invariant rules of the micro world. Our entire edifice of modern science and technology, from nanotechnology to astrophysics, now rests on this quantum foundation. The journey that started with the pharaoh's forearm now ends in the humming precision of a laboratory, listening to the silent, fundamental music of the universe. But if our units are now perfect and eternal, what frontiers of measurement remain? What grand mysteries are we still trying to quantify? The heartbeat of our digital world is a number so precise it feels almost magical. 9,192,631,770. This is not a lottery figure, but the exact count of oscillations within a single atom that now defines 1 second of our time. To understand how we reached this point, we must rewind to when time was not counted, but felt. Our earliest ancestors measured time by its flow, not its tick. A sundial traced the slow arc of a shadow, a silent conversation between Earth and Sun. The water clock, or clepsydra, marked the passage of moments by the steady drip of liquid from one vessel to another. In these devices, time was a continuous analog process, inseparable from the natural world's rhythms. It was the pendulum clock of the 17th century that introduced the idea of time as a series of discrete mechanical ticks. Its invention tied the second to the physics of our own planet, its beat governed by the constant force of gravity and the length of the swinging rod. For centuries, this was the pinnacle of precision. Yet Earth itself is an imperfect timekeeper. Our planet's rotation gradually slows due to tidal friction, and it wobbles minutely on its axis. A second defined as a fraction of a solar day was, like the meter defined from the Earth's meridian, tethered to a slowly changing reference. The quest for an invariant standard for time led science inward to the atom. Within the nucleus of a cesium-133 atom, electrons exist at specific energy levels. When exposed to microwave radiation of just the right frequency, an electron can jump to a higher level, absorbing energy. The second is now defined by counting the cycles of that specific microwave frequency that causes this quantum jump. That number, 9 billion plus oscillations, is the atomic second. This shift is profound. We no longer measure time by the grand motion of the heavens, but by the hyperregular vibrations of the subatomic world. The precision achieved is almost incomprehensible. The best atomic clocks, known as optical lattice clocks, are so accurate they would lose less than 1 second over the entire age of the universe. This incredible exactness has revealed a strange and beautiful truth predicted by theory of relativity, that time itself flows at slightly different rates depending on gravity and velocity. An atomic clock placed just 1 floor higher in a building, experiencing marginally less gravitational pull, will tick faster than an identical clock on the ground floor. The difference is vanishingly small, but these clocks can detect it. This is not just a laboratory curiosity, it is a daily correction. The global positioning system, satellites orbiting Earth each carry atomic clocks. Because they are moving at high speed and experiencing weaker gravity, their time runs faster than clocks on the surface by about 38 millionths of a second per day. If the system's computers did not constantly correct for this relativistic time dilation, the GPS in your phone would misplace your location by several miles within just a few minutes. Our entire infrastructure of global navigation, financial networks, and the internet relies on this corrected quantum heartbeat. Time, once observed in the sweep of a shadow, is now engineered from the resonance of an atom, allowing us to navigate our world by listening to the subtle warping of spacetime itself. Our tools for describing the world inevitably begin to reshape the world they describe. The transition from a sacred qubit to a quantum constant is not merely a story of increasing precision. It is a profound shift in how humanity thinks. The very structure of a measurement system acts as a silent language teacher, training minds to parse reality in specific ways. Consider the enduring legacy of the duodecimal or base 12 system embedded in inches and feet. Its deep history, stretching back to the finger-counting methods of ancient Mesopotamia, encourages a mindset comfortable with fractions. Halves, thirds, and quarters are natural divisions within 12, making it intuitive for craftsmen dividing a board or a merchant splitting a bushel. This system reflects a world built by hand, a world of practical subdivision. In stark contrast, the metric system, born from the Enlightenment, champions base 10. Its entire architecture is a cascade of decimals and powers of 10, moving seamlessly from millimeters to kilometers by simply sliding a decimal point. This design did not emerge from the workshop floor, but from the philosopher's study. It was a conscious embodiment of the age's core ideals, rationality, order, and a universal logic accessible to all. Adopting the meter and the gram was not just a technical upgrade, it was a political and cultural statement. For revolutionary France and the nations that later followed, it symbolized a break from the feudal patchwork of local traditions, a step toward a modern, unified state governed by reason. This leads us to a powerful question. Does the numerical language we inherit actually shape how we solve problems and perceive the world? A scientist trained from childhood in the metric system thinks fluidly in orders of magnitude, scaling from the atomic to the astronomical with a consistent decimal logic. An engineer working with customary units develops a strong intuition for fractional relationships and modular design. The system itself becomes a cognitive framework, an invisible set of rails that guide thought. This is why the ongoing tension between metric and imperial is so much more than a debate over conversion factors. It is, at its heart, a quiet clash of worldviews. One perspective is anchored in tradition, in the human-scale units of the body and the historical practices of a community. The other looks forward to a globally interconnected system, prioritizing seamless communication and a rational foundation derived from nature's constants. Our choice of ruler, then, is never neutral. It is a philosophical stance, a decision about whether we wish to measure the world with the echoes of the past or the universal language of the future. And if our systems of measure shape our thought, what happens when we try to measure the things that seem fundamentally unmeasurable? The precision of the Great Pyramid confronts us with a silent question. Its base is aligned to true north with an error of just 3/60ths of 1 degree, a feat that seems to demand modern instruments. How could a civilization without the magnetic compass, let alone satellite telemetry, achieve such accuracy? The answer likely lies not in lost technology, but in a profound and patient application of the sky. One compelling theory points to the circumpolar stars. Ancient Egyptian astronomers could have tracked the path of a single star, as it circled the celestial pole. By marking the star's rising and setting positions on a circular wall and bisecting the angle, they could find a north-south line of astonishing accuracy over many nights of observation. This method requires no advanced tools, only meticulous record-keeping and a deep, generational understanding of the heavens. It turns the pyramid from a mere tomb into a monument permanently anchored to the cosmos, a testament to their belief that earthly order must mirror celestial order. This same pursuit of perfection appears in a different form on the other side of the world. At the site of in Bolivia, stone blocks of andesite and granite are cut with such precise, interlocking geometries and flat, polished surfaces that they resemble modern machined parts. The conventional explanation involves incredible craftsmanship with stone tools, sand, water, and endless hours of polishing. Yet the uniformity and complexity of the cuts lead some researchers, like engineer Christopher, to question whether we have fully accounted for the techniques involved. He and others explore the possibility of advanced, yet fundamentally simple, lost knowledge, perhaps involving the use of specialized stone-cutting tools or templates that have not survived in the archaeological record. The key here is to resist the sensational leap to external, otherworldly explanations. Instead, it challenges us to expand our understanding of human ingenuity. What we label as primitive tools in the hands of a master craftsman, working within a cultural tradition that valued precision as a spiritual or political imperative, could achieve results that strain our modern assumptions. The real mystery may not be a missing technology, but a missing mindset, a scale of patience, and a collective will to achieve perfection that modern society, with its focus on speed and efficiency, has largely forgotten. This ancient precision humbles us. It reminds us that the drive to measure and build with exactness is not a product of the scientific age, but a deep and enduring human ambition, one that connects the pyramid builders to the physicists redefining the kilogram. Their legacy is a question etched in stone, asking us to never underestimate the power of careful observation, accumulated knowledge, and dedicated hands. That same drive to measure the physical world became the invisible architecture of our first economies. Long before coins jingled in a purse, value was weighed in the palm of the hand. The very earliest units of currency were not symbols, but substances, barley and silver. A shekel in ancient Mesopotamia was not a coin, it was a specific weight, a volume of grain that could be counted on to feed a family. When trade moved to precious metals, the system remained the same. A merchant's scales were his bank. The value of a silver ingot was not stamped on its face, it was determined by its mass, measured against a trusted set of stone or bronze weights. This made the standardization of weight a matter of communal survival. A market inspector's primary duty was to ensure that the bronze weight labeled 1 in one stall was identical to the 1 weight in the next. Fraudulent weights were considered a grave offense, a direct attack on the trust that held the marketplace together. This intimate link between mass and money is etched into our language. The Roman unit of weight was the libra, a word that gives us both the abbreviation for the British pound, LSD for solidi denarii, and the name of the currency itself, the pound sterling. A pound was literally a pound weight of sterling silver. The genius of coinage was that it merged the substance and the stamp. When King Croesus of Lydia issued the first standardized gold and silver coins in the 6th century BCE, he was doing more than minting money. He was transferring the authority of the public scales onto a portable, guaranteed object. The stamp of the lion, the official seal, was a promise. It said, "This disc contains exactly this much pure metal, so you no longer need to weigh it, you can simply count it." This was a revolution in trust. Value became abstracted from the slow weighing of loose bullion to the instant recognition of a sovereign's guarantee. That abstraction would only deepen over centuries, leading to paper money backed by gold, and then to today's fiat currency, which is backed by nothing more tangible than collective trust in a government and its economic policies. Yet, even in our digital age, the principle holds true. The stability of any currency, even a cryptocurrency like Bitcoin, relies entirely on the integrity of its underlying measure. For Bitcoin, that measure is not weight, but a rigorously enforced cryptographic ledger, a new kind of inviolable standard that prevents duplication and ensures scarcity. The unit of value has journeyed from a handful of grain to a line of code, but the foundational need remains unchanged: an unbreakable trust in the measure that defines worth itself. But before kings minted coins or scientists defined constants, every person carried a complete set of measuring tools with them everywhere they went. The human body was the original and most intuitive ruler. From the width of a single finger, called a digit, to the full stretch of both arms, known as a fathom, our anatomy provided a ready-made system. A palm was the width of 4 fingers, a hand was the breadth of the palm itself, and a span was the distance from the tip of the thumb to the tip of the little finger when the hand was fully splayed. The foot, of course, was the length of that very appendage, and the venerable cubit, the standard of the pharaohs, was simply the length from the elbow to the tip of the middle finger. This anthropometric system was democracy in its most basic form, universally accessible and requiring no special technology. For thousands of years, a carpenter could measure a beam with his own forearm, a farmer could pace out a field with his own feet, and a tailor could size a tunic using his client's own span. The system was deeply personal, immediate, and woven into the fabric of daily life. Yet this very intimacy was its fatal flaw. A king, well-fed and tall, possessed a considerably longer foot and forearm than a peasant who had known a lifetime of physical labor and limited nutrition. When the royal tax collector arrived to measure a field using the official king's foot, the same plot of land suddenly became larger in terms of taxable units, demanding more grain or coin from the farmer. The variability was not a bug in the system, it was a feature of feudal power. Anthropometric units enshrined physical inequality into the mathematics of commerce and law, making the strong arm of authority quite literal. This inherent lack of objectivity is precisely why these charming, human-scale measures had to be abandoned for the serious work of science and fair trade. The shift to standardized bars, and eventually to constants of nature, was a philosophical declaration that truth should not depend on whose body was used to measure it. This move symbolized a quest for a democratic standard, one that treated every person's measurement equally. And yet, the ghost of that bodily system never fully left us. We still measure the height of a horse in hands, we talk about being within a stone's throw, and we describe depth in fathoms. Even our most fundamental unit of length in one major system remains the foot, a quiet, fossilized echo of a time when we measured our world by the only standard we truly knew ourselves. A scientific idea lives or dies by a single, ruthless test. Can someone else, anywhere in the world, reproduce your results? This principle of repeatability is the bedrock of all modern science, and it rests entirely on one thing: the ability to measure with unwavering precision. Without a shared, reliable language of quantity, an experiment in Berlin becomes an unverifiable story, a personal anecdote lost in translation. The entire edifice of scientific knowledge is built on this foundation of trustworthy measurement. Consider a pivotal moment in the late 19th century. Physicists of the era were convinced that light waves, like sound waves, needed a medium to travel through. They called this invisible substance the luminiferous, a static sea that filled the universe. If it existed, then the speed of light measured on Earth should vary slightly depending on whether you were moving with or against this current. In 1887, Albert and Edward designed an apparatus of breathtaking sensitivity to detect this variation. Their tool was an interferometer, which split a beam of light and sent the parts on perpendicular journeys before recombining them. If the light traveled at different speeds along the two paths, the recombined beams would create an interference pattern, a telltale fingerprint of the wind. The precision required was almost unimaginable. They were measuring distances smaller than the wavelength of light itself, seeking a shift that theory predicted would be minuscule. After meticulous preparation and measurement, they found nothing. No shift, no wind, just a profound and unsettling null result. This failure to measure a predicted difference was, in fact, one of the most successful experiments in history. Its precise null result became a cornerstone for theory of relativity, which discarded the entirely and redefined space and time. The experiment demonstrates a profound truth: Science often advances most dramatically not when we measure what we expect, but when we build tools precise enough to measure the absence of what we expected. Every leap in understanding follows a leap in measurement. Galileo's observations of pendulum swings required him to measure time more carefully than anyone before, using his own pulse and later, water clocks, to establish the swing. The discovery of the double helix structure of DN relied on Franklin's precise X-ray diffraction images, which were essentially meticulous measurements of molecular angles and distances. Even the detection of gravitational waves in our century was the ultimate measurement challenge, sensing a ripple in spacetime that compressed a 4-kilometer-long laser beam by a distance 10,000 times smaller than a proton. The story is clear. We cannot think beyond the precision of our tools. The evolution of measurement is not a sidebar to the history of science. It is the main narrative. It is the story of humanity sharpening its senses, building ever finer lenses through which to interrogate the silent, mathematical heart of reality. The silent mathematics of a sunflower holds a secret. Look closely at the pattern of its seeds, and you will see two sets of spirals, one curving clockwise, the other counterclockwise. Count them. You will almost always find two consecutive numbers from the sequence, a series where each number is the sum of the two before it, like 1, 1, 2, 3, 5, 8, 13, and so on. This is not a decorative accident. It is a geometric solution to a packing problem, allowing the plant to fit the maximum number of seeds into the smallest space as it grows. This same mathematical rhythm echoes in the curve of a nautilus shell, the arrangement of scales, and even the sweeping arms of spiral galaxies. The ratio derived from this sequence, approximately 1.618 to 1, is known as the golden ratio, or phi. For centuries, artists and architects have been captivated by its pleasing proportions, but its prevalence in nature suggests something deeper. It points to an inherent efficiency in growth, a kind of pre-programmed measurement that optimizes form and function without a conscious designer. This reveals a startling idea. Measurement, in its most fundamental sense, is not a human invention. It is a principle woven into the fabric of the living world, a natural tool for organizing matter and energy. This biological imperative to quantify extends into behavior. A honeybee returning to the hive performs an intricate movement known as the waggle dance. The angle of her dance relative to the vertical comb indicates the direction to a food source relative to the sun. But the duration of the waggle run conveys precise information about the distance. A longer dance means a farther journey. The entire colony acts on this communicated measurement, efficiently allocating its foragers without a single map or number. Similarly, migratory birds navigate across continents using an innate celestial clock and compass. They measure the position of the stars and the sun, and even detect subtle variations in Earth's magnetic field, performing feats of navigation that would challenge a human with charts and instruments. These are not learned systems in the human sense, but inherited, hardwired programs for processing spatial information. They demonstrate that quantification is a fundamental biological strategy for survival, a way to translate the chaos of the environment into actionable data. Our own story, then, takes on a new dimension. The human development of formal measurement systems, from the royal cubit to the atomic clock, is not a departure from nature. It is a spectacular extension of this ancient, biological drive. We are not imposing an artificial order upon a wild world. We are amplifying a natural instinct to navigate, to build, and to understand our environment through proportion and relationship. Our rulers and scales are sophisticated tools that externalize and refine this innate capacity. When an architect employs the golden ratio, they are tapping into a pattern that sunflowers discovered millions of years ago. When a sailor uses a sextant, they are performing a conscious, precise version of what a bird does by instinct. Our quest for perfect standards is, at its heart, the same imperative that guides a bee to communicate distance, a relentless biological need to make the world measurable, predictable, and navigable. We have simply given that instinct a name and built for it a temple of science. This realization blurs the line between the natural and the engineered, suggesting that our greatest intellectual achievements are, in a way, a flowering of a seed planted by life itself. But if measurement is so deeply rooted in biology, what happens when we try to apply it to the most subjective realms of human experience? Can we truly measure a feeling or quantify the value of a moment? This quiet temple of measurement stands in France, a suburb of Paris. It is not a place of ancient relics, but of living agreements. Here, at the International Bureau of Weights and Measures, scientists from across the globe convene to maintain the one language that unites all nations in purpose, the International System of Units, or SI. Think of it as the modern Esperanto of reality, a carefully constructed vocabulary of 7 base units from which every other measurement flows. These are the meter, the kilogram, the second, the ampere for electric current, the Kelvin for temperature, the mole for amount of substance, and the candela for luminous intensity. This is not merely a list, it is an interconnected web. The beauty of the system lies in its coherence. A joule of energy, for instance, is not an arbitrary number, it is defined as 1 kilogram meter squared per second squared, elegantly linking mass, length, and time. This creates a self-consistent universe of calculation where units convert seamlessly, eliminating the need for messy conversion factors that once plagued engineers and scientists. The BIPM is the guardian of this language. Within its laboratories, national measurement institutes from over 100 member states collaborate, comparing their most precise realizations of these units against one another. They debate refinements, validate new techniques like the Kibble balance, and ensure that a volt measured in Tokyo is identical to a volt measured in Berlin or Ayers. In a world often divided by politics and culture, this represents an extraordinary, sustained act of international cooperation. It is a silent testament to a shared human belief that for trade to be fair, for science to be true, and for technology to connect us, we must all agree on the meaning of a centimeter, a second, or a degree. The SI system is the ultimate fruit of that centuries-long quest for a rational foundation. It has fully divorced itself from the sacred body of the king and the soil of any single nation, anchoring itself instead in the democratic constants of the universe. This global framework is the invisible infrastructure of our modern world, the reason a microchip designed in California can be manufactured in Taiwan and function perfectly in a device assembled in Germany. It is the culmination of our journey from 1,000 local forearms to a single, shared understanding written in the fundamental language of nature itself. There is a final, unbreakable wall in our quest for perfect knowledge. As science turned its most precise instruments inward, toward the subatomic realm, it encountered a paradox that redefined the very act of measurement. In the 1920s, physicists proposed a principle that stands as one of the most profound insights of modern science. It states that at the quantum level, you cannot know everything with absolute certainty. Specifically, you cannot simultaneously know both the exact position and the exact momentum of a particle, like an electron. The more precisely you pin down where it is, the more its speed and direction blur into uncertainty. The harder you try to measure how fast it's moving, the less you can say about where it is located. This is not a failure of our technology. It is not because our microscopes are too crude or our sensors too slow. This uncertainty is a fundamental property woven into the fabric of reality itself. To understand why, think of measurement not as a passive glance, but as an interaction. To see anything, you need light. To see something as tiny as an electron, you need to hit it with a particle of light, a photon. That photon, however minute, carries energy. When it bounces off the electron and into your detector, telling you the electron's position, the collision itself gives the electron a kick, changing its momentum in an unpredictable way. You have gained one piece of information at the cost of disturbing the other. The universe, at its most fundamental scale, refuses to be a detached spectator sport. The observer is always a participant. This revelation turns centuries of scientific philosophy on its head. Since the time of Newton, the dream was of a clockwork universe where, if you could know the position and momentum of every particle, you could predict everything. This principle declares that such perfect knowledge is fundamentally, eternally impossible. It places an absolute and mathematical limit on precision. The quest that began with the pharaohs, seeking perfect order through sacred cubits, now culminates in this elegant, unsettling truth that the bedrock of reality is not certainty, but probability. The universe at its core is not a collection of tiny balls with fixed trajectories. It is a realm of waves and potentials, where particles exist in a haze of possible states until an act of measurement forces one possibility to crystallize into fact. This does not make science futile, far from it. It simply redefines the goal. We are not uncovering a pre-existing, fully determined reality. We are engaging in a conversation with a universe that responds to our questions, but always retains an element of mystery. The drive to measure, which once sought to impose divine order on a chaotic world, now humbly accepts that a whisper of that original chaos is written into the laws of physics. The walls of uncertainty are not the end of our story, but a gateway to a new frontier. The quest for precision has leaped from the tangible world of atoms into the intangible realm of information itself. We no longer measure only with rulers and scales, we measure with light and logic. Our fundamental units have expanded to include the bit, the irreducible unit of digital choice, and the byte, its practical cousin. We quantify the flow of information in megabits per second, and the raw power of computation in floating-point operations per second, or flops. These are the new currencies of our age, and their standards are not forged in metal, but defined through rigorous international consensus by bodies like the Institute of Electrical and Electronics Engineers and the International Telecommunication Union. This is digital metrology, the science of measuring the invisible infrastructure that now underpins civilization. The tools of this trade are a far cry from the surveyor's rod. An engineer today peers into the heartbeat of a microchip with an oscilloscope, tracing the rise and fall of voltages measured in billionths of a second. A network specialist uses a protocol analyzer to dissect the flow of data packets, ensuring each bit arrives intact and on time. These instruments measure ephemeral patterns of electrons and photons, the silent language of our connected world. Perhaps the most profound expression of this shift is the concept of the digital twin. Imagine a jet engine, a power grid, or even an entire city. Engineers now create a living, breathing virtual replica of that physical system, fed by a torrent of real-time sensor data. Every vibration, temperature fluctuation, and pressure change in the real object is measured and mirrored in its digital counterpart. This twin is not just a static model, it is a dynamic simulation used to predict where, optimize performance, and run what-if scenarios without ever touching the physical machine. The creation of a faithful digital twin is the ultimate act of measurement, requiring the capture and synchronization of millions of data points with exquisite accuracy. It represents a complete inversion of the ancient process. Where the pyramid builders measured the earth to impose a celestial order in stone, we now measure the physical world to recreate it perfectly in the realm of information. The core mission, however, remains unchanged. We are still quantifying the world with obsessive accuracy, but our focus has expanded from the geometry of objects to the very patterns of energy and data that define how those objects behave and connect. This invisible web of measurement is what allows a surgeon to operate remotely with robotic precision, or a scientist to model the climate of an entire planet. We have built a mirror world of numbers, and our ability to navigate it depends entirely on the integrity of our new digital rulers. The atomic second, defined by the steady hum of microwaves, was once the pinnacle of precision. Yet in quiet laboratories today, a new generation of timekeepers is emerging, so accurate they could reshape our conception of reality itself. These are optical atomic clocks. While the traditional cesium clock counts microwave oscillations, optical clocks use visible light, with waves that oscillate 100,000 times faster. The atoms of choice are now elements like strontium or ytterbium, held nearly motionless in traps of laser light and cooled to temperatures just a whisper above absolute zero. This extreme control allows scientists to read the atom's natural vibrational frequency, its ticking, with almost unimaginable fidelity. The projected accuracy is staggering, an error of less than 1 second over the entire age of the universe, more than 30 billion years. This is not merely an incremental improvement. It is a leap into a new regime of measurement, where time itself can be parsed into slices so thin they challenge our very language for describing duration. The logical next step is a profound one, the redefinition of the SI second. Just as the kilogram was liberated from a physical artifact, the second may soon be untethered from cesium and re-anchored to the optical frequencies of these new clocks. This change would ripple through every technology that depends on precise timing, from satellite networks to financial trading systems, making them exponentially more reliable. But the implications run far deeper than engineering. Such phenomenal precision turns a clock into a scientific instrument of extraordinary sensitivity. It can detect the faintest whispers of gravity. According to theory of general relativity, time runs slower in a stronger gravitational field. An optical clock is so sensitive that raising it by just 1 centimeter, altering the gravitational pull by a minuscule amount, would produce a measurable change in its tick rate. This means arrays of these clocks could map Earth's gravitational field with unprecedented detail, revealing hidden aquifers, mineral deposits, or shifts in oceanic currents from space. For navigation, it promises a future where positioning is accurate to the centimeter without reliance on fragile satellite signals. Perhaps most tantalizingly, these clocks offer a new way to test the bedrock laws of physics. Some theories suggest that the fundamental constants of nature, like the fine structure constant, which governs the strength of electromagnetic forces, may not be perfectly constant over cosmic time or space. By comparing optical clocks based on different elements over years or across vast distances, scientists could hunt for infinitesimal drifts in these constants. Finding such a drift would be a revolution, a crack in our current model of the universe. This relentless pursuit of a better second reveals a beautiful, recursive truth. Our quest to measure time more perfectly is what allows us to ask deeper questions about time itself. Each new order of magnitude in accuracy is not an end point, but a new lens. It opens windows into realms we previously could only theorize, from the warping of spacetime to the possible evolution of physical law. The story that began with sundials and water clocks continues, not toward a final answer, but toward an ever-expanding horizon of inquiry, where the tool of measurement and the object of discovery become one and the same. A broken stone ruler lies half-buried in the dust of a forgotten city. It bears no label, no inscription declaring its length. Yet, to a metrological archaeologist, this silent artifact is a shouting witness. Deciphering the measurement systems of lost civilizations is a form of high-stakes detective work, where the clues are etched in brick, stone, and clay. How can we possibly know the exact length of a Roman piece or the true span of a Sumerian cubit when no perfect standard has survived? The answer lies in a meticulous, reverse-engineering puzzle. Scholars do not search for a single, pristine master ruler. Instead, they look for repetition. They analyze the dimensions of thousands of standardized bricks from a single period, knowing that consistency in size implies a shared unit. They measure the spacing between the column drums of a Greek temple, understanding that architects worked in whole numbers and fractions of their local foot. They scour ancient administrative texts, where scribes might record that a warehouse was 60 cubits long and 20 cubits wide, and then they go and measure the foundation stones of that very warehouse. Each of these data points is a vote, and when thousands of votes align, the lost standard begins to emerge from the noise with remarkable clarity. One of the most compelling cases comes from the great cities of the Indus Valley civilization, like and Harappa. Excavations there have revealed a stunning uniformity. The bricks used in construction, though found in cities miles apart, conform to a strict ratio of 4:2:1 in their dimensions. More strikingly, detailed analyses of the city's layouts show that major streets and buildings were positioned at regular intervals based on a single, tiny unit of length, approximately 1.32 inches. This was not a casual approximation. It points to a centralized system of weights and measures, enforced across a vast region, revealing a society with a powerful, bureaucratic grasp on standardization. This forensic metrology does more than just give us a number. It opens a window into the mind of a civilization. The choice of unit, its subdivisions, and the things chosen to be standardized all tell a story. A culture that standardizes brick sizes is prioritizing monumental architecture and civic planning. One that standardizes weights for precious metals is engaging in sophisticated long-distance trade. Each recovered unit is a linguistic key, helping us translate the silent language of ruins into a story of technological capability, economic reach, and administrative control. The rubble of an ancient market, when measured with this understanding, transforms. It ceases to be a jumble of stones and becomes a speaking archive, its very geometry whispering tales of merchants haggling over weighed silver, of surveyors laying out plots with knotted ropes, and of a shared belief that order measured order was the foundation of a functioning world. The giant Emir was not just a monster in the Norse sagas, he was a living ruler. From the soles of his feet to the crown of his head, his immense body provided the raw material from which Odin and his brothers measured out the world. His flesh became the soil, his bones the mountains, his blood the seas, and his skull the dome of the sky. This is more than a creation myth, it is a profound statement about the nature of reality. The world itself, in this view, is a measured artifact, its very dimensions derived from the proportions of a primordial being. This narrative pattern echoes across ancient cultures. In the Babylonian epic, the goddess Tiamat represents the formless, chaotic ocean. When the god Marduk defeats her, he does not simply destroy her, he meticulously dismembers her. From her divided body, he measures and constructs the orderly cosmos, stretching her skin to establish the heavens and anchoring them with precise dimensions. In both stories, creation is not an act of making something from nothing. It is an act of imposing limits, of defining boundaries, of carving proportion and structure out of boundless potential. This is the mythological root of measurement, a divine metrology. These myths encode a fundamental human intuition that order itself is born from the act of setting a standard, of saying, this far and no further. Before there were cubits or kilograms, there was this narrative understanding that to create a habitable world, whether cosmic or civic, one must first measure it. The gods in these stories are the first surveyors, the first architects, using the raw material of chaos to lay down the foundational lines of existence. This mythological framework provided the conceptual soil from which practical measurement systems could grow. If the universe itself was established through divine measurement, then it followed that human society, to be in harmony with that cosmic order, must also measure its own affairs with care and reverence. The temple built to exact dimensions mirrored the heavens measured by Marduk. The king's law based on a standard cubit echoed the order Odin carved from Ymir's bones. Myth, therefore, was humanity's first theory of metrology. It answered the why long before the how was fully worked out. It established measurement not as a mundane tool, but as a sacred principle, a fragment of divine power granted to humanity to continue the work of creation on a smaller scale. These ancient stories remind us that our drive to quantify and define is not merely technical. It is deeply woven into our oldest attempts to explain where we are and how a world of things and distances came to be. The ruler and the scale, in their earliest conception, were not just instruments of trade, but tiny echoes of a god's first act, tools for weaving a little human order into the vast and silent fabric of space. A perfect error is a priceless gift to science. The platinum meter bar, forged in 1799, the culmination of an epic struggle, was not quite perfect. Their heroic survey, it was later understood, contained a tiny miscalculation. They had based their work on an imperfect model of the Earth's shape, not fully accounting for its polar flattening. The meter they defined was therefore off by about 0.2 of a millimeter, a hair's breadth over its entire length. This was not a failure, it was an essential step. That minuscule discrepancy became a nagging question that drove a century of more refined geodesy, pushing scientists to map the planet with ever greater care. The same story unfolded with the kilogram. The unsettling drift detected between the official prototype and its copies was not a scandal to be hidden. It was a clarion call, a physical proof that the old system of artifact standards had reached its limit. These so-called mistakes are the engine of metrological history. Each time a standard proved to be mutable or a measurement revealed an unexpected flaw, it forced a crisis. And from each crisis came a leap. The need for better standards drove the invention of new alloys, like the platinum iridium used for the kilogram, chosen for its legendary stability. The search for more precise comparisons led to balances of astonishing sensitivity, capable of weighing a single virus. Ultimately, the frustration with physical objects that could change at all pushed the entire scientific community toward a more radical solution, anchoring units to the immutable constants of physics. This is the hidden rhythm of progress. It is not a straight line from ignorance to truth, but a spiral of successive approximations. Each generation builds the most perfect standard it can conceive, using the best tools and knowledge available. Then the next generation, with sharper eyes and finer instruments, finds the tiny cracks in that perfection. They do not discard the work of their predecessors, they use its imperfections as a precise map of where to look next. This process is the living embodiment of the scientific method itself, a relentless, self-correcting dialogue with reality. Our current international system of units, defined by the speed of light and constant, represents the most stable and universal framework we have ever devised. But to think of it as a final answer would be to misunderstand the entire journey. It is simply our generation's best approximation, a magnificent resting point built upon centuries of corrected errors. The silent promise of those quantum constants is that they will never drift, but our understanding of them, and our ability to measure them, most certainly will. Somewhere in a laboratory today, a scientist is measuring a constant with a precision that would have been magic a decade ago, and in that measurement, they may find the faintest whisper of a discrepancy. And if they do, the spiral will turn once more, not in defeat, but in celebration, because the quest has never been for a perfect answer. It has always been for a better question. Your morning coffee is a miracle of measurement. The water heated to just below boiling by a thermostat, the grounds measured in scoops or grams, even the steep time counted in minutes, all follow an invisible recipe of precision. This is not high science, but it is applied science, a daily alchemy performed in kitchens and workshops around the world. When a baker follows a recipe, they are conducting a controlled chemical experiment. The exact ratio of flour, water, yeast, and salt, measured in cups or grams, determines whether the result is a dense brick or an airy loaf. That teaspoon of baking soda is not a suggestion. It is a calculated reagent that will react with acid to create carbon dioxide bubbles and lift the batter. These humble tools, the graduated cup and the set of spoons, are the direct descendants of the merchant's scales and the apothecary's weights. They bring laboratory-grade consistency into the home, turning an uncertain art into a repeatable process. The same quiet precision guides the craftsperson's hand. A woodworker marking a board with a pencil, and a metal rule is engaging in a tradition that stretches back to the architects of the pyramids. That simple tape measure, with its etched lines for inches and centimeters, contains the entire history of humanity's struggle to standardize length. Each precise cut, each drilled hole placed at a measured interval, relies on a shared language of dimension that ensures parts will fit together. A seamstress creating a garment works from a pattern, a map of angles and curves built entirely from measurements. The difference between a piece that drapes perfectly and one that bunches awkwardly can be a matter of a few careful eighths of an inch. These acts feel mundane, almost instinctual, but they are profound. They represent the complete democratization of precision. The power to measure consistently, once guarded by priests in temples and later by scientists in national institutes, now lives in a drawer in your kitchen or hangs from a hook in your garage. This silent infrastructure of measured daily life is the ultimate triumph of that long evolution. It means that complex technology, consistent results, and beautiful craftsmanship are accessible to anyone. You do not need to understand the quantum definition of a second to use a timer, or comprehend constant to follow a recipe measured in kilograms. The centuries of intellectual struggle have been distilled into simple, reliable tools. This is how grand revolutions settle into the fabric of existence, not as lofty theories, but as the quiet confidence that your bread will rise and your shelf will be level. The world is rendered predictable, one careful measurement at a time. The ancient marketplace was not just an economic space, it was a moral arena. Among the earliest written laws we possess, a clear and recurring command appears: you must not cheat with your scales. The Hebrew Bible explicitly forbids carrying two sets of weights in your bag, one heavy for buying and one light for selling. Centuries earlier, the Code of Hammurabi prescribed severe penalties for merchants who used inaccurate measures. This was not merely a regulation about commerce, it was a foundational statement about justice. In a world where most trade was face-to-face, an unfair measure was a direct, intimate theft, a betrayal of the community's trust that allowed the powerful to exploit the vulnerable. The standardization of weights was therefore a profound ethical act, an attempt to build fairness into the very tools of daily life. When a society agreed on a single shekel, or it was creating a level field, however imperfect, where a day's labor could be exchanged for a guaranteed amount of grain or silver. This moral thread, woven into the fabric of civilization, never frayed. It simply evolved. Today, we call this legal metrology, the science of ensuring that every measuring instrument used in public trade is accurate and trustworthy. A team of inspectors no longer checks bronze weights in a bazaar, but they do calibrate the digital scales at your supermarket, the fuel dispenser at the gas station, and the electricity meter on the side of your home. Their work is invisible, but its purpose is ancient, to prevent a modern form of the same old deception. When you pay for a liter of gasoline, you are relying on a chain of custody that stretches back to a national measurement institute and ultimately to those quantum constants. That guarantee is what allows commerce to function at a global scale. We can order goods from across the planet with confidence because a kilogram in a warehouse in Shanghai means the same thing as a kilogram on your doorstep. This system of enforced honesty is the quiet guardian of a fair society. It transforms measurement from a simple act of quantification into a pillar of social contract. The struggle for perfect standards, then, is not only a scientific pursuit. It is also a continuous effort to build a world where transactions are transparent, where value is not stolen through clever manipulation, and where the basic trust required for a community to thrive is encoded, quite literally, in the calibration of its instruments. The dream of the lawgivers of antiquity is alive in the hum of a certified fuel pump, a silent promise that the balance shall be held true. Beyond our atmosphere, the familiar language of meters and kilometers collapses into absurdity. The distance to our own moon is a staggering 384,000 kilometers, a number already difficult to grasp. To the nearest star, it is about 40 trillion kilometers, a figure so large it becomes meaningless noise. For the cosmic scale, astronomy demanded a new grammar, a unit born from the geometry of our own orbit. That unit is the parsec, a term blending parallax and, it is defined as the distance at which one astronomical unit, the average Earth-Sun distance, subtends an angle of 1. In simpler terms, it is a measure derived from stellar parallax, the apparent shift in a star's position when viewed from opposite sides of Earth's orbit. To measure a star 1 parsec away, you observe its position against the distant background, wait 6 months for Earth to travel to the other side of the Sun, and observe again. If the star appears to have shifted by 1/3600th of a degree, that tiny angle of 1 confirms its distance. This elegant method turns Earth's yearly journey into the arm of a cosmic caliper, allowing us to step out into the galaxy. But what happens when we wish to speak not just to the stars, but to whoever might live near them? In the 1970s, as the Pioneer and Voyager spacecraft were launched on trajectories that would carry them beyond our solar system, scientists faced a profound communication challenge. How do you explain human scale and time to an intelligence that shares no history, no culture, and no anatomy with us? The answer was etched onto golden plaques and records. They did not depict a ruler. Instead, they provided a universal key, a fundamental constant of nature. The most critical diagram on the Pioneer plaque shows the transition of neutral hydrogen, the most common element in the universe. When the spin of a hydrogen atom's electron flips relative to its proton, it emits a radio wave with a specific wavelength and period. This transition is a clock and a ruler built into the fabric of space itself. By graphically defining this hydrogen transition, the plaque says, "This is our unit of time, and this wavelength is our unit of length." Any technological civilization capable of intercepting the probe would understand this physics, allowing them to decode the human figures, the location of Earth, and the launch date etched alongside it. This is perhaps the ultimate expression of our metrological journey, a message that abandons all earthly artifacts in favor of a pure, universal constant. Yet, as we dream of reaching such destinations, we confront a universe where measurement itself becomes fluid. Theories of relativity are not abstract equations, they are practical engineering manuals for interstellar travel. As a spacecraft approaches a significant fraction of light speed, time for those aboard slows relative to observers back on Earth. Lengths in the direction of travel contract. A navigational computer programmed with Earth-based units would give false readings, because the meter and the second it uses are no longer the same as those at home. For a civilization traveling between stars, the only reliable measurement foundation would be one anchored in local physical constants, like the speed of light or constant, which remain invariant for all observers. Our current shift on Earth to such a constant-based system, then, is not merely a scientific refinement. It is a necessary step in a much grander evolution. We are, in a very real sense, developing the native language for a future cosmic community, a lexicon of measurement divorced from any one planet, ready for the day when humanity, or its messages, truly learn to speak across the light years. Yet, for all its power, the language of measurement remains silent before the deepest mysteries of existence. We can quantify the chemical signals of affection, map the neural pathways of a thought, or analyze the mathematical ratios in a sunset, but the essence of what we feel in those moments slips through the net of numbers. Love, beauty, a sense of meaning, the raw fact of consciousness itself, these are territories that defy any universal unit. They are qualitative, not quantitative. This is the final, clarifying frontier in our long journey. The sacred cubit of the pharaoh was more than a length, it was a bridge to the divine, a tool meant to imbue human creation with cosmic meaning. It measured stone, but it pointed toward spirit. The modern meter, defined by the speed of light, makes no such promise. It is a tool of breathtaking purity, designed explicitly to describe the how of the universe, the mechanisms and relationships, with perfect impartiality. It is silent on the question of why. This is not a failure of science, but its precise and necessary focus. By rigorously excluding the unmeasurable, science gained the power to build a shared, objective understanding of the physical world. That clarity allowed us to split the atom, to connect continents with data, and to listen to the birth of stars. The evolution from sacred to scientific measurement represents humanity learning to separate two profoundly different ways of knowing. One seeks to describe the objective, repeatable fabric of reality. The other grapples with the subjective, unique experience of being alive within it. Our mastery of the quantitative realm is a monumental achievement, a story of patience and genius that has given us unprecedented control over our environment. But the qualitative realm, the world of value, feeling, and purpose, remains the eternal domain of poetry, philosophy, and personal faith. These are not opposing forces, but complementary lenses. A physicist can measure every wavelength of light in a painting, while an artist captures the emotion it evokes. A neurologist can chart the brain activity of a musician, while the listener is transported by the beauty of the song. The journey of measurement shows us where the map ends and the territory of lived experience truly begins. It reminds us that we are the only creatures who build clocks to count seconds, and also the only ones who can feel a moment last forever. Our greatest tools have defined the world we share, but the meaning we find within it is a measure we each must take for ourselves. This arc from sacred arm to quantum constant is a map of the human mind itself. We started by projecting our own bodies and our gods onto the cosmos, seeking order in the length of a king's bone or the sweep of a star's path. We navigated a wilderness of conflicting feet and stones, a chaos that finally sparked a revolution, a desire to anchor our world not in tradition, but in nature. That drive led us to tie the meter to the curve of the earth, a majestic idea made real through hardship and dedication. Yet even our planet proved an imperfect anchor, prompting the creation of that perfect, silent cylinder, the kilogram, a masterpiece of metal that became its own kind of lonely oracle. Its inevitable, microscopic drift was the final necessary lesson, pushing us to look beyond things altogether. We learned to listen instead to the universe's own heartbeat, to the speed of light and the tick of atoms, finding in physics a language of constants more permanent than any stone or sovereign. This is not merely a chronicle of better tools. It is the story of how we slowly, painstakingly, learned to separate our description of reality from our hopes and fears about it. We externalized our senses, building instruments that could see farther and weigh finer than any human hand, creating a shared vocabulary of precision that allows a scientist in Tokyo to perfectly understand an experiment from Toronto. That shared language is the invisible foundation of everything around us now. It is the reason your smartphone connects across continents, why medications are consistently potent, and how we can send a rover to Mars with the confidence that its measurements will be meaningful. The quest for the perfect measure is, at its heart, the relentless human pursuit of a common truth, a truth built not on decree, but on demonstrable, repeatable fact. We now stand in an era where the most fundamental units of our reality are defined by the quantum realm, by numbers so constant they are believed to be the same everywhere in the universe and for all time. With optical clocks so precise they can detect the gravitational warping of a single centimeter, we are not ending this story. We are writing its most exciting chapter yet. So the next time you glance at a clock, bake from a recipe, or follow a turn-by-turn navigation, pause for a moment. You are interacting with the culmination of this entire epic. You are touching a legacy of curiosity that stretches back to the first person who compared their shadow to a stone, a living thread that connects you to pyramid builders, Enlightenment surveyors, and modern physicists. This journey shows that our greatest triumphs often lie in agreeing on the simplest things, on the shared definitions that allow us to build a world together. If this exploration of hidden connections resonated with you, I would love to hear which measurement mystery fascinates you most. Was it the encoded astronomy of the pyramids, the lonely kilogram in its vault, or the quantum leap to defining mass with light? Share your thoughts in the comments below. For more journeys into the profound stories hidden in plain sight, don't forget to subscribe. Thank you for measuring this time.